Hi everyone, so the topic of this video is to show why L1 minimization is a linear program. So just as a review, what is a linear program? And that's pictured here in this green box here. So a linear program has a fixed B, C, and A such that I am minimizing a linear cost function. So just take that vector C, dot it with some prospective minimizer x with two constraints. The first constraint is that ax is less than or equal to b for some matrix A, some vector b, and that I have non-negative coefficients in x. So the question is, if I take L1 minimization of ax minus b over x in Rn, and here A can be in Rm by n and B is in Rm. Is there a connection between these two? Is there a B, C, and A such that I can cast this minimization problem over here on the left into that one, into something of that form? And so I'll show you guys how to get that. So first of all, what we can do is rewrite this problem as the minimum over all v subject to v equals ax minus b. And that's just direct substitution, right? It's substituting v equals ax minus b, and then putting it in a constraint equation. So it's slightly different, but clearly the same. Clearly they give you the same answer, right? So recall that this is going to be the sum of the absolute value of the components. And so if I let the vector 1 be this vector of all ones, then I can rewrite this as the minimum over v of 1 dotted with v. Sorry, not over v, over an auxiliary vector t, such that the absolute value of vi is less than or equal to ti, and that v equals ax minus b. Furthermore, we can rewrite this equation. This can just be recast as vi is less than or equal to ti, vi is less than or equal to ti, and v equals ax minus b. Okay, and now you can see here, since t is now what we're minimizing over, this constraint v is actually just a dummy variable. We don't really need it at this point. So I'm going to rewrite this as 1 dot t, and I'm going to write minus ax minus b, and I'm going to subtract t to the other side. So remember that these less than or equal to and greater than or equal to's in this context mean component-wise. It means for every I, the components are less than or equal to 0. And notice that this constraint, I put this constraint that the absolute value of vi is less than or equal to ti. That implicitly tells us that t is greater than or equal to 0. Okay, and then this, these constraints here, essentially a linear program basically says linear cost function with linear constraints. And that's basically what we look like here. So we don't have it quite in the form there in green, but for now, we can rewrite this, but I'm going to hold off on that for a bit. So we'll do that at the very end. So you can trust me that that's a linear program, because we'll come back to it. So this is equal to the minimum here. Okay, so something I forgot to mention here. We can view minimum over V. Oh yeah, so sorry. I forgot a minimum over X here. Okay, so when I did this, right, I want X to now be part of the constraints. So I have to have it be fixed in order to solve this. So there's really a min X everywhere here. Sorry about that. So you can view this almost as g of x. I'm doing minimum of x of g of x, because I can solve this optimization problem for fixed x. So once x is fixed, that's a constraint, and I can solve it. So my problem is really the minimum over all x and t of 1 dot t. And then same constraints. Those will just be directly copied. Okay, so I'm going to do one more trick here. This will be the final trick to get it into this green form. So if you're satisfied here and you say, okay, these are clearly linear constraints because A is a matrix, then you can stop the video here. If you want to see all the details of how you get it into this form, that's the remainder of this video. So what I'm going to now do is rewrite this as alpha dot z of let's do minus ax minus t is less than or equal to, so minus b is positive b, then we subtract it over, that's minus b. Ax minus t is less than or equal to positive b, and pz is greater than or equal to 0, where z is equal to x and t, alpha is equal to all zeros, so n zeros, and then the same one vector, n of them, p is equal to 0, 0, 0, and the identity, n by n identity. Okay, so that's just direct algebraic change here. So I'm doing a optimization over 2 Rn vectors. Well, that's the same as an optimization over one vector in R2n. And then I just slightly rearrange alpha and p to fit my constraints. Okay, so I'm going to do one more step here. Again, this is just algebraic manipulation, just to prove to you guys that this is indeed a linear program. So then this is equal to b, z is less than or equal to beta, pz greater than or equal to 0. This is where b equals, and I'm going to get this b, its first row is going to come from this equation, and its second row is going to come from that equation. Similarly for beta. So just directly translating these, and you can pause the video because this is just algebra here. So if this is going too fast, pause the video and see if you can fill in these details. And then beta, again, is just going to come from the right-hand side over here. This is negative b, less than or equal to beta. And there's one more step. So here in the green that you see, we need z greater than or equal to 0, but right now we have pz greater than or equal to 0. So this is actually very convenient So this is just going to be, I'm essentially just going to skip a step on you guys. So this is the minimum over z, alpha dot z, bz is less than or equal to beta. And I'm just going to say, well, that's z is greater than or equal to 0. Why can I do that? So remember that p is given over here. So it says I'm going to constrain the second component, in other words, t that we were looking at, to be greater than or equal to 0, but I don't have any constraint on x, what we're calling x. But remember that alpha, the objective function, is not affected at all by x, the first n components of z. So we can throw in any constraints we want. It doesn't change the objective function at all. So these two optimization problems are equal. And that shows it. This is the canonical linear program form. Thank you.